So we're going to continue talking about functions and the graphs of their derivatives, which has to do with their slopes. Derivatives are the slopes of the tangent lines. And so in lesson 18, we talked about using the slope or the secant line slope to find the instantaneous rate of change or the derivative at a particular point. So we took the limit as x approached whatever that point was, and we could find the derivative using a calculation or an equation. So again, this is going to be back to a little bit of a subjective lesson. So just bear with me because we're going to have to do some estimations here. But we're going to see how the slope of the tangent line creates a graph that is related to the function graph itself. So we're going to choose a few points on our graph here. So I'll do like -2, since that's the first place that we can actually see a value here. We'll do -2 and go over here to 4. So I'm going to make us a little t-chart over here. So -2, -1, 0, 1, 2, 3, and 4. And what we're going to find for y is really the derivative at that point. So these are just going to be estimates. Estimate the derivative at each of these points. So starting at -2, you don't actually have to draw the line in. For this one, I think I'll go ahead and draw a line. But I may not draw them all. I may just use this little piece of paper so that we can see. And so what we want to do then, once we draw in a tangent line there, is to kind of count the slope. And it looks like it goes up 1, 2, 3, 4, and over 1. So a slope of about 4. Now that's what we're going to do at each of these, but I think, you can draw them all in if you want. If you draw them all in, I would make my lines maybe a little bit smaller, so that they're not interfering with each other. But either that or just use the card and kind of estimate, or use a piece of paper. But at -1, we're going up 1, 2, and over 1. So maybe a slope of 2. At 0, our tangent line is just flat, so that's a slope of 0. At 1, that's not a very good line, but it looks like it goes up, maybe up 1 over 1, so maybe a slope of -1. Again, these are just estimates. At 2, though, looks like that's going to be another place where we have a flat line slope, so a slope of 0. And then at 3, looks like it's going maybe up 1 over 1, or maybe up 1 over 2, whichever one you want to pick. I'll just say up 1. Up 1 over 1. Alright, and then 4, I think another one of those steep slopes. Looks about like that one, so we'll just say about a slope of 4. So what we want to do down here on the bottom is we're going to take those points and we're going to graph them. So I'm going to rewrite those so we'll have them down here where you can see them as we graph them. So we had -2, 4, -1, 2, 0, 0, 1, -1, 203144. All right, so let's go ahead and plot those points. I've got -2, and then 1, 2, 3, 4. -1, 2, 0, 0, 1, -1, 2, 0, 3, 1, 4, 4. All right, so it looks kind of like a V, depending on the spacing here. And like I said, these were estimates, so it's not really super accurate. But if we join these together, it's really supposed to be a curve. So maybe we didn't estimate on a few of those exactly right, but it should be a parabolic looking curve. So let's talk about that. Look at this graph up here. This graph was a cubic function graph. We know from the shape of it, and because if I were to multiply these together, I'd have an x cubed graph. And then when I took the derivative, I got an x squared graph. That is not coincidental. So keep that in mind, because you're going to be estimating the slopes just like I did on some of your homework. And so if your graph is a parabola, then when you get your set of points, it should form a pretty good line down here. Or if this is a fourth power function, your derivative should look similar to a third power function. So you'll kind of know if you're on the right track when you're estimating your slopes.